Alright, in this video we're going to be doing mole to mass stoichiometry questions as well as mass to mole stoich questions. So just as a quick reminder here about the 4 steps of stoich that we're going to be going through. Step 1, always write your balanced chemical equation. Step 2, get your moles of your given substance or the substance you have the most information for. Step 3, use your mole ratio to convert moles of your known into moles of your unknown. And then step number 4, answer the question, essentially. Okay, so for this first example, we're asked to calculate the mass of iron produced in the decomposition of 8.95 moles of iron 3 oxide. So step 1, let's work on our balanced chemical equation. So we're told that we have a mass of iron produced. So iron, that's going to be one of our products. We're also told that this is a decomposition reaction. Okay, so this is a product. I'll worry about that later. Okay, but we're told that this is the decomposition of iron 3 oxide. So this is going to be a reactant. So that's where I'm going to be starting. So iron 3, so remember that these Roman numerals, they indicate the charge of a multivalent metal. They do not indicate how many atoms of that metal you have. Okay, so we have iron 3 plus oxide. So oxide ions, they like to have a 2 minus charge because they are part of, let me go to my periodic table here. So oxygen, that's part of group 16, and non-metallic ions in group 16 like to have a charge of 2 minus. Alright, so because 3 minus 2 does not equal 0, we have to do crisscross applesauce. So that's why I'm going 2 here and then 3 over here. Alright, so now that compound is balanced, so we're good to go on that. Now, the question doesn't mention anything about the state of this iron 3 oxide, but since it's an ionic compound, and since the question doesn't mention anything about temperature, we can assume this is room temperature, and whenever an ionic substance is at room temperature, unless the question specifies otherwise, you can assume that it is going to be a solid. So, long story short, ionic compounds, if the question doesn't give you any further details, assume that your ionic compound is solid at room temperature. Alright, so since it's a decomposition reaction, what happens in those is you have a compound, it breaks apart into its elements. So that's why I'm going reaction arrow right now, and we're told one of the products is iron, and iron is a solid at room temperature. Okay, the other product must be oxygen, because again, we're just taking this and breaking it up into the elements that make it up. Remember though that oxygen is part of Hofbrinkel, so whenever it's by itself, there's always 2 of them. And oxygen is going to be a gas at room temperature. You can check that out on your periodic table. Alright, so we have our skeleton equation. Let's make sure it's balanced. Okay, so I'm looking at this and I'm going to say that oxygen is likely going to be the trickiest one to balance. If you're looking for some pro tips on like how to figure out where to start, ultimately it doesn't really matter where you start. You're going to get the same answer in the end. However, there are spots where it's a little bit easier to start or to balance your equation if you start in a certain spot. Okay, the reason why I chose oxygen is because of this subscript 2 here. Okay, which means that it might make it a little harder to balance oxygen. Okay, whereas iron over here, there's just one atom of iron here. So that's going to be easier to balance in the end. Okay, so I have 3 oxygens going in, 2 coming out. So I need to figure out, okay, what is the lowest common multiple between 3 and 2? Well, that's going to be 6. So what times 3 is equal to 6? 2 times 3 is equal to 6. And what times 2 is equal to 6? 3 times 2. All right, so this 2 doesn't just affect oxygen, it also affects iron. So we have 4 irons going in, we need 4 coming out. Okay, so our irons are balanced and our oxygens are 2. Okay, we got 6 going in, 6 coming out, we're good. All right, let's organize our information. So we're asked to calculate the mass of iron. So mass of iron, we have no clue. Okay, and we're given the moles of iron oxide, or sorry, iron 3 oxide. So let's write that over here. Okay, now typically wherever you have mass, you are going to need molar mass. The reason being is because the formula that deals with mass and moles is mass is equal to moles times molar mass. So that's why I'm saying whatever you have, or whatever you have the mass for, or you're looking for the mass, you are going to need molar mass. Okay, so you might as well get that out of the way and figure it out early. So the molar mass for iron, we're going to need to look at our periodic table and find iron. So iron is number 26. The molar mass is 55.85. And the units for molar mass is grams per mole. All right, now that we got all of our information organized, let's start figuring this out. So again, balanced chemical equation, we've figured that out. Moles of our given, we were given that in the question. So now we're on step 3, mole ratio. Okay, so 8.95 moles of iron 3 oxide times by a fraction sign. So now this is the mole ratio. So what we want is iron. What we are given is iron 3 oxide. Okay, so these cancel out because I'm just treating iron 3 oxide kind of like a unit. So if you have the same unit in the top and the bottom, they're going to cancel out. All right, so essentially what we're doing is we're taking 8.95 and timesing it by 4, then dividing by 2. Or in other words, you could also just say 8.95 times by 2. It'll get you the same answer, okay? Because 4 divided by 2 just simplifies to 2. So 8.95 times by 4 divided by 2, 17.9. So that's 17.9 moles of iron. I'm not going to worry about sig digs right now because I'm not finished the question. Okay, because we want mass of iron. We do not want moles. So I'm going to follow this equation here. And maybe I will scooch this up a little so it's right underneath my formula. So we got mass of iron is equal to our moles of iron times by our molar mass of iron. So keep in mind, moles and molar mass, they have to belong to the same substance. That's why I insist that you write out the identity of your substance so that you never lose track of what you are talking about. Because oftentimes I find students just get some blinders up when they start dealing with questions and just number crunching, and they forget the actual substance they're working with, and then they used the wrong molar mass. All right, 55.85 grams per mole. Okay, so if we take a look at this, we have moles on the top and the bottom, so they are going to cancel out. So mass is equal to, so let's go 17.9 times by 55.85, and we're going to get 999.715. And that's going to be grams of iron. All right, so now since we're talking about a final answer, now we're going to care about significant digits. Okay, so our only number given to us has 3 sig digs in it. So we're going to want to report our final answer in 3 sig digs. So if I count 1, 2, 3, my cutoff line is right on the decimal there. And the 7 after the cutoff line is going to round up everything in front of it because they're all 9s there. So this is actually going to round up to 1,000. Okay, but the problem here is that 1,000 isn't 3 sig digs. So you've got 2 options here. Okay, you can either turn 1,000 into scientific notation, or instead of grams, you can report it in kilograms. The reason why we can do that is because the question didn't specify units for mass. Okay, so let's go grams and then I'll show you both ways. So if you wanted to turn it into scientific notation, you would go like this. So the decimal, when it's not written, it's at the end of the number. So for scientific notation, you want to make it so that there's only 1 digit to the left of the decimal. And then however many come after it just kind of depends on significant digits. Okay, and then you're going to go times by 10 to the power of some exponent. Now, this exponent, it's going to be positive if your original number is bigger than 1, which is our case. But just want to cap this conversation off. Your exponent would be negative if your original number is somewhere between 1 and 0. Okay, so this is a very quick refresher about scientific notation. We have talked about this earlier in this course. Okay, so scientific notation for 1,000, you could do 1.00 times 10 to the power of 3, because we would have moved our decimal over 1, 2, 3 spots over to the left. And this would still be in grams. Okay, if you wanted to report your answer in kilograms and still have it in 3 sig digs, well, 1,000 grams is just 1 kilogram. Okay, so 1 kilogram, and that's in 3 significant digits. So either or is acceptable. All right, next example. What mass of carbon trinitride solid is required to burn and react with 0.35 moles of oxygen gas? So burn, that's the key word that tells us that this is a combustion reaction. So carbon trinitride, and it's a solid, so I'm writing it as a solid. Since it's a combustion reaction, it's burning in the presence of oxygen, which is a gas, and it's O2 because oxygen is a diatomic element. All right, now let's predict our products. So you can imagine that oxygen is reacting with each individual element of our fuel, okay? And it's going to create the most common oxide with each of those elements. So the most common oxide with carbon is carbon dioxide. And the most common oxide with nitrogen is nitrogen dioxide. So keep in mind you are going to have to know the most common oxides that oxygen forms. With substances, you can go back to the video about combustion reactions to see what that would look like. Okay. All right, we have our skeleton equation. Let's make sure that this is balanced. So we have 1 carbon going in, 1 coming out. Great, that is balanced. 3 nitrogens going in, 1 coming out. So let's put a 3 right there. So that 3 didn't just affect the nitrogen, also affected the oxygen. All right, so for the product side, we have 2 oxygens coming from carbon dioxide, and we have 3 times 2, so 6, coming from nitrogen dioxide. So in total, that's 8. Okay, so 8 is a number that is divisible by 2, which is good because we can go, okay, well, 4 times 2, that's equal to 8. So now we have 8 oxygens going in, 8 coming out. That's balanced. All right. So step 1, balanced chemical equation, done. Let's organize our information. So we got 0.35 moles of oxygen gas. Okay, and we're asked what mass of carbon trinitride. So mass, we don't know. And anytime you're looking for mass of a substance, you're going to want the molar mass. Okay, so now we got to do a quick review of how to figure out molar mass. So we're going to find each element on the periodic table. So carbon is 12.01, nitrogen is 14.01. And you're going to want to break it up into each element, how many atoms of each element you have, and the molar mass of each of those elements. So we just said, okay, carbon's 12.01 and nitrogen is 14.01. We have 1 atom of carbon because there's not a subscript number, so there's an invisible 1. And we have 3 atoms of nitrogen. Okay, so now we have our totals column. So mathematically what we're doing is we're going, okay, 1 times 12.01, that's going to give us 12.01. 3 times 14.01, that's going to give us 42.03. Okay, and what we're doing with the totals column is we're adding everything up. So 42.03 plus 12.01, that's going to give us 54.04, and that's grams per mole. Okay, so I will write that over here. All right, so that was a quick refresher of how to calculate molar mass for a compound. So let's get started on solving this now that we have all our background information. So we already have our moles of our given substance. So I'm going to write that down. And now we are at step 3, mole ratio. So I'm going to take this, times it by fraction sign. So what we want is carbon trinitride. So there's 1 carbon trinitride. What we're given is oxygen, and the coefficient in front of oxygen is 4. Okay, so what we're doing is we're taking 0.35 times by 1 divided by 4. Okay, so you could go times by 1 divided by 4, or you could just go 0.35 divided by 4. It'll give you the same thing. Okay, so we have 0.0875 moles, and right now, since oxygen canceled out, we have moles of carbon trinitride. All right, how much room do I have? Okay, I think I'll be able to squish this underneath. So now that we have our moles, we need to figure out our mass. So mass is equal to moles times molar mass. Our moles is 0.0875. Molar mass, That's 54.04. And that's grams per mole. So looking at the units, moles is on the top and the bottom, so they cancel out. So that will give us 4.7285 grams, and that's grams of carbon trinitride. Let's look at sig-digs. So this number has 3 sig-digs in it. So where they count is 1, 2, 3. So I'm going to have to move this over here. 3 sig-digs. So that means our cutoff line is 1, 2, 3 right there. So then our final answer is going to be 4.73 grams of carbon trinitride. All right, next example here. In the neutralization of sulfuric acid, so neutralization, that's a specific word that means you have an acid reacting with some base. Okay, so ultimately what this means is it's going to be a double replacement reaction. So in the neutralization of sulfuric acid, 4.56 moles of a sodium hydroxide solution was used. What mass of water would be produced in this reaction? So let's write out this reaction. So sulfuric acid, so ic acid, I ate something icky, so ate ick. So sulfuric acid, what my memory device means, I ate something icky, means you turn sulfuric, you turn the ick part back into 8 to figure out what your anion is. And then you're going to put as many hydrogens will balance out the charge of your anion. Okay, so that's why this is going to be H2SO4, and acids are always aqueous. Plus sodium hydroxide, solution means aqueous. All right, now we are told that water is being produced in this reaction, but let's just go through what's happening here. Okay, so as I've said previously, for double replacement reaction, which just means you have a compound reacting with a compound to produce 2 new compounds. What I like to do is I like to focus on the cations or the positive ions and just switching places with those. And remember, the subscript does not necessarily come along for the ride. The whole point of subscripts is just to balance the compound. Okay, so hydrogen is going to take the place of sodium, and that's where we're getting our water. Okay, HOH versus H2O, they're the same thing. Since this occurs at room temperature, because the question doesn't specify that it occurs at any other temperature, we're going to say this is liquid. Remember, water is never aqueous. At room temperature, it's always going to be a liquid. All right, so that's our first product. Now let's figure out the product with sodium. So sodium went over here to live with sulfate. So we have sodium sulfate. Okay, so sodium is a group 1 ion. It likes to have a +1 charge. Sulfate has a 2- charge. You can look that up on your periodic table with the table of polyatomic ions. Okay, 1 - 2, that's not 0, so we got to do crisscross applesauce. So I'm going to put a 2 behind sodium there to balance it out. All right, so we got to figure out what the state of sodium sulfate is, and we can do that by looking at our solubility table. So sulfate is right here. Don't get sulfate confused with sulfite. They look very similar, but they are 2 different things. So sulfate says most things are soluble, but let's just double check and make sure sodium isn't in our list of exceptions. Looking down here, sodium is not listed, therefore, yep, it is going to be very soluble. So that means we rate it as aqueous. Okay, so we got our skeleton equation. Let's balance this out. Okay, so we've got 2 hydrogens coming in, and how I'm going to treat water is it's a hydrogen and hydroxide together. Okay, so just so you know, so I'm focusing on this hydrogen right here. The reason why I'm doing that is because it makes your life easier if you're just focusing on balancing polyatomic ions and treating them as one unit to balance. Okay, that's why I'm doing what I'm doing. So 2 hydrogens coming in. I only have 1 hydrogen right here coming out. This one's a hydroxide, so I'm going to put a 2 right there. Okay, so the hydrogens are balanced. Okay, now that 2 didn't just affect hydrogen, it also affected hydroxide. So we have 2 hydroxides coming out. I need 2 hydroxides coming in. So we got that 2 not just affecting hydroxide, also affecting the sodium. So hydroxides and hydrogens are balanced. Now I'm going to worry about sodium. So we got 2 sodiums coming in, 2 coming out. That's balanced. 1 sulfate going out, 1 sulfate coming in. That's done. All right, let's organize our information. We've got 4.56 moles of sodium hydroxide. Okay, and we're asked what mass of water. So that's going to be this. So mass of water, we have no clue. The molar mass of water, so we have 2 hydrogens. So if we look up hydrogen, the molar mass of that is going to be 1.01. So 2 times 1.01 is 2.02, plus we got to take into account oxygen. So 2.02 plus 1 oxygen, that's going to give us 18.02 grams per mole. All right. So we got our balanced chemical equation, we got our moles of our given, and we're at step 3, use your mole ratio to convert moles of given to moles of unknown. Okay, so what we want is water. What we're given is sodium hydroxide. Now if you take a look at this, 2 divided by 2, that simplifies down to 1. Okay, 1 times anything is going to be the exact same number. So this is going to equal 4.56. And that's moles of water now, because if you treat sodium hydroxide like a unit, it cancels out because you got 1 on the top, 1 on the bottom. So we're talking about water. We're not done just yet. We need to figure out mass of our water. So mass is equal to moles times molar mass. Our moles of water is 4.56. Molar mass is 18.02. So if we multiply those 2 numbers together, we're going to get 82.1712. Okay, and our units, so moles cancels out, we're left with grams. Looking at our question, our given number is in 3 sig digs, so that's what our final answer needs to be in. So our cutoff line is 1, 2, 3. Cutoff line is right there. So our final answer is 82.2 grams, and that's going to be of water, which you can either rate as HOH or H2O, either or. All right. There's some practice questions here which you can do later, but let's move on to mass to mole stoichiometry examples. So before we did mole to mass, now we're doing mass to mole. All right. So example number 1, determine the amount of moles of oxygen required when 12.2 grams of cyclopentane, which they give us the chemical formula for, is burned completely. Okay, so burned, that means that this is a combustion reaction, so it's some fuel plus oxygen gives us products. Okay, now since it is a hydrocarbon for our fuel, that means that our products are going to be carbon dioxide and water vapor. Now, just a reminder, hydrocarbon just means that the substance is mostly made out of carbon and hydrogen. And for the context of Chem 20, hydrocarbons for this class are usually just carbon, just hydrogen. Okay? But if you take more chemistry in the future, that definition changes just a little bit. Okay? All right, so cyclopentane, C5H10, and it's a liquid, burns in oxygen. Remember Hofbrinkel, oxygen is diatomic. And we're going to get carbon dioxide, gas, and water vapor. So let's balance. We got 5 carbons coming in, 5 carbons coming out. So for combustion reactions, remember balance carbon first, then hydrogen, then oxygen. 10 hydrogens coming in, I want 10 coming out. For oxygens, 5 times 2, so we got 10 from here, and we got 5 times 1, 5 from here, so we got 15. So there's a problem because we're only ever going to get even numbers here. But our trick is, take this number, divide it by 2. So 15 over 2. Now the other problem is, for stoichiometric calculations, you want whole numbers for your coefficients. So how are we going to get rid of this fraction? We're going to times everything by 2. So times by 2, so that's going to give us 2 molecules of C5H10. 15 over 2 times by 2, well, 15 times 2, that's 30. 2 times 1, that's going to be 2. That equals 15. Okay, if you wanted to do that the quicker way, what you could do is you could be like, well, 2's on the top, 2's on the bottom, those cancel out. Guess what? I get 15. All right, so we got 15 oxygen. Okay, 5 times 2, that is going to give us 10 for both carbon dioxide and water vapor. Done. All right, let's organize our information. So they gave us mass of cyclopentane. So mass, cyclopentane, 12.2 grams. So remember what I said, anytime you're given the mass of something, you need to figure out the molar mass of it. So molar mass, you can pause the video and figure it out for yourself. Molar mass of cyclopentane is going to be 70.15 grams per mole. All right, and we're asked to determine the amount of moles of oxygen. So this is what we're looking for. All right, so essentially with these questions, we are just doing what we did before, just backwards. So we're starting with this formula to get our moles of our given substance, or the substance we have the most information given for. Okay, then we are going to do our molar ratio, and we will get our answer. Okay, so we're still following these 3 steps of balanced chemical equation, find the moles of your given. We just need that mass is equal to moles times molar mass equation to get the moles of our given substance there. Okay, and then afterwards we're going to do mole ratio, and then step number 4, give the question what it's asking for. All right. So mass is equal to moles times molar mass. Okay, but the problem here is we want to figure out what moles is. So if I'm rearranging this equation, so I want to get moles by itself. Okay, what's preventing moles from being by itself is that it's being multiplied by molar mass. So the opposite of multiplying is division. So I'm going to divide both sides by molar mass. So mass divided by molar mass is equal to moles. Okay, that is the formula that I'm using here. And I'm just going to switch it around. Okay. All right, so mass of cyclopentane, that was 12.2 grams, divided by 70.15 grams per mole. Okay, so if you're wondering how the units cancel out, it's a little bit easier to look at this same thing just written slightly different. So if I take 12.2 grams and then if I divide it but write it like division like this, grams and then moles would go up here. Okay, so essentially what you're doing is you're taking 12.2, okay, and then timesing it. If you really want a number here, you would put 1. So 12.2 times by 1, and then you are still dividing it by 70.15. So what I'm trying to say is this is the same as this, okay? So I'm just showing you this other way just to show you how the units cancel out. So grams is on the top and the bottom, so that's how you know you're left with moles. All right, so grams, those cancel out, and 12.2 divided by 70.15, that's going to be 0.17391. Now, keep in mind this number keeps on going on forever, so I'm going to go ... and write moles. So, now we got our moles of our given substance. Now we need to take our mole ratio and use it to convert our known substance moles into our unknown substance moles. So let's do that in purple here. So we got 0.17391, goes on forever, moles, times by, actually I'm going to write the identity of the substance here, so that was cyclopentane, times by, so molar ratio, what you want, divided by what you given. Okay, so we are given cyclopentane, and we want oxygen. Okay, if you treat cyclopentane kind of like a unit, these cancel out. Okay, so we're taking our 17.391, timesing it by 15, dividing by 2. So let's just show this entire calculation from start to end. So if I'm going 12.2, another reason why I'm doing this is to get the entire number. Okay, so I have this. Okay, and another point I want to illustrate to you is that I'm going to use this entire raw number in this next calculation. I am not going to round it early because then that will introduce inaccuracies into your answer. So I'm going to go times by 15 divided by 2 equals, so we get 1.3043, goes on forever. To mean goes on forever. All right. So in terms of sig digs, this has 3 sig digs, so our answer needs to be in 3 sig digs. So I'm going to count from the far left, 1, 2, 3. There's my cutoff line. So 1.30, and that's moles of oxygen. Done. Okay, example number 2. Determine how many moles of oxygen gas is produced when 10 grams of calcium phosphate decomposes completely. Okay, so this tells you that it's a decomposition reaction, and since it's saying calcium phosphate decomposes, this is the substance that is your reactant that's breaking apart into its elements. So calcium and then phosphate is PO4. You can double check that on the table of polyatomic ions in your periodic table. So phosphate likes to have a -3 charge. Calcium is a group 2 ion, so it's likes to have a 2+ charge. So we got to do crisscross applesauce to balance out the charges here. So we got 3. And then to represent that we have 2 phosphates, I'm going to put phosphate in brackets and write a 2 there. Okay, so any polyatomic ion, when you have more than one of it, put it in brackets. All right, so it doesn't mention anything about the state of calcium phosphate, but we do know that it is an ionic compound, and that ionic compounds at room temperature, they are going to be solids. All right, so it's decomposing, so it's breaking apart into its elements. So the elements that make this up are calcium, which is a metal, and at room temperature, that's going to be a solid. Plus, we have phosphorus. Remember, whenever phosphorus is by itself, it's a polyatomic element. And whenever it's by itself, there's 4 of them together. And phosphorus is also a solid at room temperature. So how I'm figuring out the states of these elements is I'm going to the periodic table, I'm checking out the color, I'm saying, okay, that's green. Green means non-metallic solid. For calcium, it's yellow. Yellow means a metallic solid. So that's how I'm getting the states there. Okay, my last product is going to be oxygen. Oxygen's blue, which means it's a gas. Reminder, oxygen is a diatomic element, so whenever it's by itself, there's always 2 of them. All right, so that's our skeleton equation. Let's balance this. Okay, I'm thinking that perhaps phosphate or oxygen is probably going to be the more tricky ones. I'm just going to start with phosphate, with phosphorus. Okay, so looking at the phosphate ion, I got 1 times 2. So this 2 affects everything inside of these brackets. So I have 2 phosphoruses on the reactant side. Okay, and I got 4 coming out. So I'm going to go 2. So what's going to happen is I'm going 2 times the 2 phosphates here. Okay, so I got 4 coming in, 4 coming out. For oxygens, now I have 4 times 2 times 2. So 4 times 2, that's 8. 8 times 2, that's 16. So I have 16 oxygens here. That means I need 16 coming out. So 8 times 2, that's going to be 16. All right. Calcium, we have 2 times 3, so that's 6. So I need 6 coming out because I got 6 going in. All right, now everything's balanced. Now let's organize our information. So we got 10 grams of calcium phosphate, so mass 10 grams. Let's figure out our molar mass. Okay, so again, break it up into each element, figure out how many atoms of each element there are, and then multiply how many atoms of each element in this compound by its molar mass. And once you have the molar mass total for each element, you just add them all up for your compound. Okay, so you can pause the video, figure that out. All right, so since this is a bit more of a complicated one, I'm just showing my process here. Okay, so we had 3 atoms of calcium. The molar mass of a calcium atom is 40.08. So 3 times 40.08 is going to be 120.24. For phosphorus, we have 2 of them because we have 2 times the 1 phosphorus, part of phosphate there. Okay, so 2 times 30.97 is going to be 61.94. And with oxygens, we have 2 times 4, so that's 8. So whatever you do, do not take the coefficient into account when you are figuring out your molar mass, okay? You only worry about the coefficient for the mole ratio. You do not worry about the coefficient when you are calculating molar mass. The reason being is because the units for molar mass is grams per 1 mole, not grams per 2 moles, just 1. So that's why you do not worry about the coefficient when you are calculating the molar mass for any substance. Okay. So for oxygen, like I said, we have 8 times by molar mass of an oxygen atom, which is 16, which is going to give us 128. So if we add up all of these here, we are going to get 310.18 for our molar mass. And that's grams per mole. Okay. So step 1 did a balanced chemical reaction. Step 2, we need to figure out moles of our given. And I'm just going to write out what we're looking for. So determine how many moles of oxygen gas. So moles, we got no clue for oxygen. All right, let's go back here. So moles, I'm going to use what we figured out over here. So moles is going to be equal to mass divided by molar mass. Okay. So we got 10 grams divided by 310.18 grams per mole. So the grams cancels out. And we are going to get, so 10 divided by 310.18, we're going to get 0.03223, goes on forever. So that's our moles of calcium phosphate. Okay. Now I'm just going to go straight into my mole ratio just to save on space. So we have 2 calcium phosphates and we want oxygen, which has a coefficient of 8. Okay, so ultimately we're taking this entire number and essentially just multiplying it by 4. How am I getting 4? Because I'm going 8 divided by 2 is 4. So let's put that into our calculator. So times by 4. Okay, so we get 0.1289, goes on forever. And that's moles. So, looking at the question, this number given to us is in 3 sig digs. So I need to put my answer in 3 sig digs, so I'm counting 1, 2, 3. There we go. Remember, leading zeros do not count as significant. All right, so that's going to leave us with 0.129, and that's moles of oxygen. All right, next one. How many moles of hydrogen gas is produced when 13.7 grams of aluminum reacts with water? Okay, so I'm going to focus on that last part there. aluminum reacts with water. So these two substances are your reactants. How do you know? Because of the words reacts with. Okay, so let's get that started. We've got aluminum, which is a solid at room temperature, and that is reacting with water. I am going to write it as HOH to make life easier to figure out what our products are going to be. Okay. Although we are given what one of the products are because it says hydrogen gas is produced. Okay. But you should know how to do this process even if you aren't told what one of the products are. All right, so if you have an element reacting with a compound, that is going to be a single replacement reaction. So what that means is you need to figure out, okay, what type of ion does the element like to form? Well, aluminum likes to form ions with a 3+ charge. Okay, so since it likes to form positive ions, I'm going to switch aluminum with something else in the compound that likes to form positive ions. So with water, keep in mind I'm treating it as hydrogen and then hydroxide. Okay, so I'm going to be switching aluminum with the first hydrogen. They are switching spots. Okay, so what I'm going to get out of this is aluminum's going to live with hydroxide, so that's aluminum hydroxide. Aluminum likes to have a 3+ charge, hydroxide likes to have a 1-, so that doesn't equal 0. Got to do crisscross applesauce. So we want to say we need 3 hydroxides because hydroxide is a polyatomic ion. We need to put brackets around it when there is more than one of them. All right, so now that's balanced. And I will worry about the state later. Now, hydrogen went and took the place of aluminum, so it's by itself now. Hydrogen, Hofbrinkel, it's a diatomic element. And we know it's a gas because you can look that up in the periodic table, but it also says it's a gas, hydrogen gas. All right, now let's worry about, okay, what state is this? Okay, the reason why I'm worried about state is because I'm like, oh, this was put in water, so this could be dissolved in water. So let's take a look. So let's find our anion or our negative ion first. Hydroxide. Okay, group 1 ions and ammonium, they are soluble, but everything else is insoluble. So aluminum isn't in either one of these groups, so that means it must be insoluble. So this is solid. All right, that's our skeleton equation. Let's balance this out. Okay, I'm going to start with hydrogen. Actually, let's do hydroxide first, because why not? All right, so we got 3 hydroxide coming out and only 1 going in. So I'm going to put a 3 right here. Okay, hydroxide, that's done. So 3 hydrogens, 3 hydroxides. But wait a second. H2, we're only ever going to get even numbers. So let's go back to the drawing board. Okay, let's see if we can go. We did have a 3 here, but we need this to be an even number. So what's the lowest common multiple between 3 and 2? Well, that's 6. So I'm going to increase this to 6. Okay, so now we have 6 hydrogens, and I can go put a 3 here so that that will be 6 hydrogens coming out. But now I also have 6 hydroxides coming out. So if I put a 2 right here, I will have 6 hydroxides coming out. Okay. All right. So hydroxides and hydrogens, they're taken care of. Now we need to worry about aluminum. So we have 2 aluminum coming out. We need 2 going in. Done. So for single replacement reactions, the best thing to do to help yourself with balancing is leave the element to the very end. The element that only has one atom making it up. Okay. Over here, the hydrogen, yeah, that's an element, but it's a diatomic element, so I didn't leave it to the very end because it's a little bit more complicated. All right, we got our balanced chemical equation. Let's arrange our information here. So we got 13.7 grams of aluminum here. The molar mass for aluminum, that's going to be 26.98 grams per mole. It asks us how many moles of hydrogen gas. So moles, hydrogen gas, we got no clue. All right, let's get rocking and rolling with this. So moles is equal to mass divided by molar mass. Let's substitute in our numbers. So 13.7 divided by 26.98 grams per mole. So when I divide those two numbers, 13.7 divided by 26.98, that's going to be equal to 0.5077, goes on forever. And that will be moles of aluminum. All right, I'm just going to jump straight into my mole ratio here. So I'm given aluminum and we want hydrogen. Okay, so coefficient for hydrogen, that's 3. Coefficient for aluminum, that's 2. So we're taking our number and we're not rounding it, timesing it by 3, dividing by 2. So times by 3 divided by 2. Okay, so we get 0.7616, goes on forever. And that's moles of, aluminum's cancel out, moles of hydrogen. All right, sig digs. We got 3 sig digs, so our answer needs to be put in 3 sig digs. So I'm going to count from the far left. The first 0, because it is a leading 0, does not count for sig dig. So 1, 2, 3. There's my cutoff line. So my final answer is going to be 0.762 moles of hydrogen. All right, last example for this section here. Silver metal reacts with nitric acid to produce nitrogen dioxide, silver nitrate, and water. Okay, so since this is a more complicated reaction, they're giving us more information about the reaction. How many moles of nitric acid would be required to produce 5 grams of a silver nitrate solution? All right, step 1, balanced chemical equation. So silver metal reacts with nitric acid. Those are our reactants. So silver metal, nitric acid. So we're ending with ic acid. So that means the polyatomic ion ends in 8 because I ate something icky. So where's nitrate? Right there. Okay, so I'm going to balance out this -1 charge with a single hydrogen. So that's HNO3. And acids are always aqueous. Okay, now it says it's going to produce nitrogen dioxide, which is a gas, plus silver nitrate. So silver has a +1 charge, nitrate has a -1 charge. It's already balanced. Okay, and water, which I'm going to write as H2O this time. You could write it as HOH if you really wanted to. All right, with this because water is present in this reaction, we do got to double check what the solubility is on this. Okay, so if we go to our solubility table, too far. So nitrate, that is right there. Okay, most things are soluble, but we got to make sure, is silver nitrate here? No, so it is very soluble. So it is aqueous. Okay, let's balance. All right, so looking here, the hydrogen is grabbing my attention, so that's where I'm going to choose to start. Okay, so we got 1 going in, 2 coming out. I'm going to put a 2 right there. Okay, so we got 2 hydrogens going in, 2 coming out. So the 2 didn't just affect the hydrogen, also affected the nitrate. So I'm looking here, and we got nitrate here. But one thing I'm going to caution here, because this is a more complicated reaction, okay, than our typical single replacement, double replacement, combustion, formation, decomposition, I'm going to caution you against treating polyatomic ions as a single unit for balancing with more complicated reactions like this case. Okay, because if I did that, I'd be like, well, there's 2 nitrates. I only have 1 here, so I'm going to put a 2 there. However, let's just focus on the nitrogens for a second. Okay, so I got 2 times 1 nitrogen going in. So I got 2 nitrogens going in, and I have 1, 2 coming out. So I actually don't need to worry about the nitrogens right now. Okay, so hydrogens are balanced, nitrogens are balanced. Let's check out oxygen. We got 2 times 3. So we got 6 oxygens over here. We have 2 plus 3, so 2 plus 3, and then plus 1 more. That's equal to 6. So oxygens, they are balanced out as well. That's great. Okay. Now, last but not least, silver. We got 1 going in, 1 coming out. It's already balanced. Moving on. Okay, so how many moles of nitric acid? So this is what we have no clue. Would be required to produce 5 grams of silver nitrate solution. So mass, silver nitrate, 5 grams. Okay, so anything that involves mass, you need to figure out molar mass. Okay, so you can pause the video and figure out what the molar mass is of silver nitrate. Alright, so just to show you the background work, in order to get the molar mass for silver nitrate, this is what I've done. So I've got 1 atom of silver, the molar mass from the periodic table for each silver atom is going to be 107.87. 1 times 107.87 is going to be the exact same number. For nitrogen, we've got 1 of those, and each has a molar mass of 14.01 according to the periodic table. So 1 times 14.01 is going to give us the same number. For oxygen, we have 3 of them, times by molar mass of oxygen, which is 16. That gives us 48. So adding all of these up, we're going to get 169.88, and that's grams per mole. So I should be writing this over here. Okay. So I'm going to have to start my calculation over here. So moles is equal to mass divided by molar mass. So we got our balanced chemical equation. We need to find our moles of our given substance. So that's why I'm starting with this. So we're going 5 divided by 169.88 grams per mole. So if I do that on my calculator, 5 divided by 169.88, so we get 0.0294, keeps on going on forever. And that would be for moles, because grams are going to cancel out. Okay, so that's moles of silver nitrate, because all of the numbers we started with belong to silver nitrate. Okay, so step 2, find your moles of your given. Done. Now we're going to go to step 3, molar ratio. So we are given silver nitrate, and we want nitric acid. So the coefficient for nitric acid is 2. Coefficient for silver nitrate, that's 1. Remember, when nothing's written, there's an invisible 1 right there. Okay, so essentially we're taking this number, timesing it by 2. So we get 0.05886, goes on forever. Okay, so now we are finishing off with sigdigs because the question wants just moles of nitric acid. So 3 sigdigs. So I'm going to start counting from the 5 because these leading zeros do not count. 1, 2, 3. Cutoff line is right there. So 0.0589 moles. And this is of nitric acid. There we go.